What's up, Dan number 2?
Hey, Dan number 1. I just found out I failed my geometry test again. Another 7%.
Oh man, 7% is pretty bad, dude. You gotta work on that. How'd you miss so much of the test?
It's not my fault. I mean, it's a geometry class. I thought they were just going to ask me about like shapes and circles and stuff, but like half the test was about this thing that I'd never heard of called like Sakari Legrandre? I don't know.
You talking about Sakari Legendre?
Yeah, I don't know, man. Something like that. I don't know. It was dumb. I don't know. I don't know what I'm going to do. I might withdraw.
Don't withdraw, man. I mean, I'm sure you can understand this stuff. I took this class a little bit ago. I bet I could help you out a little bit with Sakari Legendre. All right, Dan number 2, listen up. The statement of Sakari Legendre is, if we have a triangle ABC, then the angle measure of the triangle is less than or equal to 180 degrees. It seems like a pretty simple statement, and the easiest way to prove this is going to be through contradiction. Typically, whenever we have a proof where we're trying to prove two different things, like less than or equal to, instead of showing that ABC can be equal to 180 and that it can be less than 180, we're just going to show that triangle ABC can't be more than 180 degrees. And in order to do this, we need specifically one lemma, but we're going to need another lemma to prove the first lemma that we really need. And so we're going to start by first looking at those two other lemmas. All right, so the first lemma that we're going to need in order to prove the second lemma that we actually need for our proof is called, in the book it's called lemma 4.5.3. I'm going to refer to it as sum of subtriangles. And the idea of this lemma, the statement is, if ABC is any triangle and E is an interior point of the segment BC, then the angle measure of triangle ABE plus the angle measure of ECA is equal to the angle measure of triangle ABC plus 180 degrees. So to visualize this, let's draw triangle ABC. And then let's place a point E on the interior of BC. If we connect then A and E, we now have two subtriangles. We have triangle ABE and we have triangle ECA. And we can see that these two triangles make up triangle ABC. They're subtriangles. And we're stating that the angle measure of these two subtriangles added together is equal to the angle measure of the original triangle plus 180 degrees. And you might be saying, well, isn't the angle measure of all triangles 180 degrees? That's only true in Euclidean geometry. And remember that the overall theorem that we're trying to prove, Sakari Legendre, is trying to place an upper bound on the angle measure of a triangle in neutral geometry. So we don't know that a triangle is 180 degrees. Otherwise, this is a really simple formula, right? 180 plus 180 equals 180 plus 180. But since we don't know, we haven't gone into Euclidean geometry, we don't know that for a fact. So we're going to show this relationship is true first. All right, so I've gone ahead and made our triangle a little bit bigger so it's easier to see, and then I've labeled the angles so that I don't have to write out quite as much as we do this proof. And we're going to start working with this side of the equation. We're going to turn this side of the equation into this side of the equation. So we have the angle measure of ABE plus angle measure of ECA. Well, what do we know about these angle measures? We know that they're made up, obviously, of each of the angles in the triangle. So let's go ahead and trade out these angle sums for the individual angle measures. So we have that this is equal to the measure of ABE is this one. So we're going to say measure of angle B plus measure of angle E plus measure of angle A prime. And then we have this triangle. So then we have plus the measure of angle E prime plus measure of angle C plus measure of angle A prime. Now, we know that E lies between B and C, and that the ray AE lies between ray AB and AC because of the consistency of betweenness. Because of that, we can use the angle addition postulate, and we know that A prime plus A double prime is equal to A. We also know by linear pairs that E plus E prime equals 180 degrees, since the line BC is 180 degrees, and these two angles divide that 180 degree line. So we have here E and E prime. So let's replace E plus E prime with 180 degrees. And then we also have A and A prime being added. So let's add those two up to just be angle measure of A. So then we have angle measure of B plus angle measure of C, and then this has been combined, that's been combined, that's been combined, that's been combined, and that's been combined. So we just have angle measure of B plus angle measure of C plus 180 plus angle measure of A. Well, if we bring this angle measure of A over here, we can see that these are just the three angle measures of our original triangle. So we then have the angle sum, the angle sum of triangle ABC plus 180 degrees. And that this is equal to our original statement, that the angle sums of these two subtriangles add up to this. So this is the first lemma that we need for Szekely-Legendre. It's going to be useful in proving the next lemma that we're going to use in our actual overall proof. So if you can't quite see yet how this is connected into the statement of Szekely-Legendre, that's fine. We're going to be using it in the next lemma, which will then be used in our final proof strategy. All right, so the next lemma that we're going to prove, I'm going to refer to as the angle sum preservation lemma. Recall that our final goal is to show that for any triangle ABC, its angle sum is less than or equal to 180 degrees. So this lemma states if A, B, and C are non-collinear points, and recall that if we have three non-collinear points, we can form a triangle with them, then there exists some triangle A prime, B prime, C prime, such that their angle measures are the same of the two triangles, and that the angle measure of angle A prime is less than or equal to 1/2 of the angle measure of angle A. So if we have this triangle here, ABC with angle A, all this lemma is saying is that we can build some other triangle, ABC, or rather A prime, B prime, C prime, such that this angle, A prime, is less than or equal to 1/2 of the angle measure of A, and such that these triangles have the same total angle measure, or rather angle sum. So the reason why this is going to be useful is because in our final proof, when we're showing by contradiction that Szekely-Legendre holds, it's going to be useful to be able to construct different triangles with different angle measures that ultimately have the same angle sum for the full triangle. So this is going to be useful in that case. So let's go ahead and start this by drawing a triangle ABC. And then we're also going to place a point E at the midpoint of segment BC. And we're going to construct a ray from A to E. We're then going to select a point on the ray AE, D, such that the length AE is equal to the length ED. Pretty easy. We're then going to draw in this other segment, BD. And notice that E is an endpoint for the ray EB and an endpoint for the ray EC, and that they're opposite rays. Also notice that E is the endpoint of EA and ED, and that those are opposite rays. So therefore, by vertical angles, we know that these angles are congruent. We also know that E is at the midpoint of C and B, which means by definition, these line segments are also congruent. So now we can see by side angle side that these triangles AEC and triangles BED are congruent. So we can go ahead and write that. So let's name some of these angles real quick. So we're going to have A as the overall angle at A, and then we're going to have A prime and A double prime. We're going to have similarly B, B prime, B double prime, and then we're going to have E and E prime. Perfect. So now we're going to use our prior lemma, the one that we proved before, which I named the sum of subtriangles. Because now we see that we've created two large triangles. We've created ABC and we've created ABD. And both of these triangles are split up, right? We have ABC is split into ABE and also AEC. And we see that ABD is split into DEB and BEA. We learned from the sum of subtriangles postulate that triangles, the angle measures of triangles AEC and AEB are equal to the overall sum of ABC plus 180 degrees. So we're going to subtract this 180 to this other side of the equation so that we just have angle measure ABC is equal to the angle measures of the smaller triangles, or the subtriangles rather, minus 180 degrees. And then we're going to write that exact same thing for the triangle ABD, since we know that, that this applies to that triangle as well. Now notice that this is the same triangle. This triangle is shared between both of our two triangles. And then recall from before that we found that triangles AEC and DEB were congruent. So therefore, these are the same thing as well. And then we have the same constant 180 that is being subtracted off of them. And so these angle measures must be the same, since we have the exact same triangle plus two congruent triangles minus the same constant. They must be equal. All right, so then we've shown the first part of our proof, right? We've shown that for some triangle ABC, there exists a triangle that has the same angle measure. Now we need to show that this second triangle ABD that it has some angle that is less than or equal to 1/2 of an angle of our original triangle. So that's what we're going to show next. All right, so the next part of our lemma here is all about angle measures. So we're going to be focusing on our angle measures here. The first thing to note is that, again, by consistency of betweenness and angle sum postulate, or not the angle sum postulate, rather the angle addition postulate, we know that the overall angle A is made up of the two smaller angles A prime and A double prime. So we know that this relationship is true, which we can see visually really easily. And the same thing for angle B, right? We see that it's made up of angles B prime and B double prime. So there are a couple other interesting things to note here, which is that angle A double prime is congruent to angle D up here. Similarly, B double prime is congruent to angle C up there. We also know that it must be the case that in each of these cases, with angle A and angle B, one of their component angles has to be less than or equal to 1/2 of the original angle. Why is that? Well, you can imagine that if we divide the angle perfectly in half, if we bisect it, then both of the angles, in this case, angle A prime and angle A double prime, will have the same angle measure, and therefore both of them would be equal to 1/2 of the original angle. We can see that the maximum that either of them be, if we split it right down the middle, the maximum that they can achieve is 1/2. And if we split it any other way, one angle will be larger than 1/2 of the original angle A, and the other one will be smaller than the original, than 1/2 of the original angle A. So we have this relationship that at least one of these must be less than or equal to 1/2 of the original angle A. So we then have three cases, right? We have the case where they're both equal to 1/2 of the original angle A. We have the case where A prime is less than half of the original angle A, and we have the case where A double prime is less than half of the original angle A. So let's first consider the case where A prime is less than 1/2 of the original angle A. Then angle A prime is also an angle of this other triangle, right? Of DAB, right? It's the exact same angle that is shared. And so if that is the case, if A prime is less than 1/2 of the original angle A, and A prime is also part of this other triangle, then we can just fix our triangle A prime, B prime, C prime from our statement to equal triangle ABD. In which case we have that this angle is part of this triangle, and it's less than or equal to 1/2 of the original angle A, and that gives us the other part of our statement, since we know that this triangle has the same angle measure. In the other case, where A double prime is less than or equal to, or rather less than half of the original angle measure A, well, we know that A double prime is congruent to angle D, which means if this is the case, then angle D must be less than or equal to 1/2 of the measure of angle measure A. In which case we can fix A prime, B prime, C prime to equal this triangle DAB, and therefore we've shown that our statement is true. All right, now we are officially ready to start proving Saccheri-Legendre. Except there is actually one more thing that we need. So we already have our angle sum preservation lemma that we just proved, and then we need one other fact, which is called the Archimedean property of real numbers. And all this says is that if I have one positive real number and another positive real number, I can divide the first positive real number by 2 and eventually get it smaller than the other positive real number. So let's say that you give me 10 and 2. Well, I can divide 10 in half once and get 5. And then I can divide it by 2 again and get 2.5. And then I can divide it again and get to 1.25, which is less than 2. Or if we had made this number, if we had made our first number 12 and our second number 1, divided by 2 to get 6, divided again to get 3, divided again to get 1.5, and then divided again to get 0.75, which is less than 1. So just this idea that we can divide a number by 2 a number of times to make it smaller than any other number. And again, say we had 12 and originally we had 1, we'd had to divide it 5, 6 times to get it smaller than 1. If we then change this to 0.5, we would then have to divide it again, and so on and so forth. And if we can make this number arbitrarily small, and we just have to keep adding divisors. We just have to keep dividing by 2 over and over and over again, and eventually we'll always be able to make it smaller. So we don't need to prove that, we can take that as given. So now we'll prove Szekely-Legendre. And as I said, to start this whole thing off, we're going to do this by contradiction. So we're going to assume that there exists some triangle ABC, I wrote that wrong originally, ABC with an angle measure, or rather an angle sum, that is greater than 180. And we're going to specifically define it to be 180 degrees plus some number epsilon. And epsilon can be any real number, right? It could be 10, it could be 20, it could be 1, it could be 0.1, it could be any real number. We're just going to add on to 180. And you can see that these are equivalent ways of writing something, right? We can say that ABC is greater than 180, thus it is 180 plus the additional thing, right, that makes it greater than 180. So we're going to say this is true. We're also going to say that there exists some n such that 1 over 2 to the n of times the angle measure of angle A is less than epsilon. So this is saying that there exists some number n, some natural number n, that if we multiply 1 to the 2 over n by angle measure A, then we're going to get some resulting angle measure that is less than the epsilon that we wrote up here. Yeah, no, I get that it seems a little bit confusing, but this is just our Archimedean property from earlier, right, Dan number 2? This is all we're saying here is, hey, I can divide angle measure A by 2 a certain number of times, n times, and the result is something less than epsilon, which is what we showed with the Archimedean property. So we're going to assume that this is true as well. All right, so now it's time to use our lemma, the angle sum preservation lemma. So we're going to say by this lemma, we're going to say that there exists another triangle, A prime, B prime, C prime, with these properties, that its angle sum is equal to the angle sum of A, B, C, and we're going to specifically say, as part of the second part of this statement, that it has some some angle measure, A prime, that is less than or equal to 1/2 of angle measure A. That looks kind of like our one equation we have there, that 1/2 to the n weird thing. Yeah, Dan, too. We are doing something with dividing by 2 here, right? Something similar that we're doing up here, right? So what we're going to do is we're going to apply this lemma again, and we're going to say, okay, well, this triangle A prime, B prime, C prime exists. Therefore, there's another triangle, A double prime, B double prime, C double prime, that has the same angle measure as, or angle sum as A prime, B prime, C prime, which has the same angle sum as triangle ABC. And we know by this lemma that there exists some angle measure A double prime that is less than or equal to 1/2 of the angle measure of A prime, which we know is less than or equal to 1/2 of the angle measure of A. Therefore, this new angle measure of A double prime must be less than or equal to 1/4 of the angle measure of A, since it's less than or equal to half of the angle measure, which is 1/4. So can you see that all we're doing is putting 1/2 to an increasing power? This can be rewritten as 1/2 squared mu, or angle measure of angle A. Which I can write over here if it's being blocked. All we have to do is keep applying our lemma 10 or n number of times. There exists some triangle out there that has the same total angle sum as triangle ABC, so it has the angle sum 180 plus epsilon, and it also has some angle that is less than epsilon, right? So let's draw this out. So we have here our original triangle ABC, whose angle sum is equal to 180 plus epsilon. We then have this other triangle which I'm going to call triangle A to the n, B to the n, and C to the n, that has some angle here, which we'll call angle A to the n, that we know is less than epsilon. We also know that the total sum of the angles of AN, BN, CN is equal to this same angle sum of ABC. So it equals 180 plus E. Well, let's break this down. We know that the angle sum of AN, BN, CN is equal to the sum of the measure of angle AN plus the measure of BN plus the measure of CN. And we know that the angle measure of AN must be less than or equal to, or rather, must be less than or equal to epsilon. So if we put in an epsilon here in place of that angle measure, we see that this is less than or equal to 180, or rather, I misspoke. It is strictly less than epsilon, plus epsilon. Well, if we subtract epsilon from both sides, that should be a greater than symbol because this, this angle must be less than epsilon. Well, then we're left with just the measure of BN plus the measure of CN must be greater than 180 degrees. Now, Dan, number 2, is that ringing any bells for you? Any alarm bells? Can't we not have two angles more than 180 though? That's like more than a straight line, right? You're exactly right, Dan, number 2. We cannot have two angles in a triangle that sum to greater than 180 degrees. We know from prior work and prior experience that's not possible. Therefore, we have a contradiction, and we see that it is impossible that our original triangle ABC, have an angle measure that is greater than 180. And we therefore conclude our result, which is that ABC is less than or equal to 180.